That might be fun. Let me see if I can get this Zoom bar out of my way. So this one, I mentioned before, this one I like. The idea here is that not all 40% of the people that support Trump are rabid lunatics that will follow him no matter what happens, but only a small portion of them, like maybe half of them, are the lunatics that would put up with anything, and the rest we can peel off with things like this impeachment stuff and this Syria stuff. And that may be true, so that Trump may be a non-viable candidate, even though he has this hardcore people that will never turn against him. So that looks like that's happening. Anyway, speaking of books, I heard about this thing, the Cybersecurity Canon. This has been around for a while. It came from Palo Alto Networks. This is a very interesting bunch of books. I've only read a few of these. Quite a few of them are, I see the textbooks in most of my classes in here, but these are a bunch of highly recommended cybersecurity books. So I definitely got to read a few more of these. So that's a good thing to know.
Spam Nation.
What's that?
Spam Nation's up there.
Yeah, yep, Spam Nation's up there. Many books. I mean, a lot of famous books, but there's a bunch of books I hadn't heard of up here. And probably ought to read the rest of them. So anyway, this I thought was pretty interesting. BMW has decided to paint a car with carbon nanotubes, and apparently this stuff is incredibly expensive, but it's blacker than black. So they carbon nanotubes costing more than gold or diamonds, but apparently creating the most beautiful black paint job for a car. And so I guess so. I guess that's the result. So anyway, all right. So you can register to vote online. I didn't know this. Someone pointed to this. Now, when I first saw it, they had a tweet, and I thought it meant you could vote online, which would be very interesting. But I think all you can do is register to vote online. But even that is pretty cool. I remember you used to have to do it on paper, and it used to be hard to do. So apparently everybody can just register online in California. So that would be a good thing to do. I highly recommend voting. So this is awesome, and I'd like to get the hardware and do it. Something I used to do board driving with the students. We would drive through San Francisco and pick up all the Wi-Fi signals and look at the Wi-Fi security, but I quit because it reached the point where everybody was using WPA. And so there was really no point. But the next thing would be to board drive Bluetooth, but that is very difficult because of the frequency hopping it goes through. Every Bluetooth signal is hopping in a pseudo-random way across 80 channels, so you can't follow it if you haven't paired with that device. And so you can't even tell anything about the data they're sending or what protocol they're using or anything. All you see is like the total amount of radio energy. But there are people who have been working for years at DEF CON trying to develop hardware and software to let you do this so you can pick up Bluetooth with something like Wireshark. And here's another example of this. And this guy's made a Bluetooth low energy capture the flag where you build some hardware and then he somehow has gadgets and you can test it and find things. So I'd sort of like to check this out. And there's a whole bunch of information you need to know to run Bluetooth. Bluetooth is a very complicated protocol and very insecure in the earlier versions and in many flaws. And of course, it's everywhere. So it would really be a good idea to learn more about it. And so that would be a fun thing to try. I haven't tried it yet. If anybody wants to try it.
What do you think is the range on the BLE for the low energy? It's got to be more than about 10 feet, right?
Oh, yeah, I think the range is pretty high. I'm not quite sure what the low energy. I think the low energy is spectacularly insecure, because it does something like have a shorter handshake or something. Oh. I've heard some claims. In fact, there was a recent Bluetooth attack where they said with the Bluetooth low, I think it's the Bluetooth low energy, there is a byte that determines the length of the key. And every Bluetooth is required to support key lengths down to 1 byte. So you can limit the key to a key space of 256 and then brute force it. They're supposed to be an 8-byte key, which would be pretty big, but in fact, you can negotiate 1-byte keys and then you can totally get in. And that's in the fundamental protocol. It's not a bug of an implementation. So that's pretty awesome. And so this could be me. There was a Michigan college course in voting security, and they hacked a voting system that was in use. But they had a bug bounty program. And the bug bounty program said you could try to hack it. So the teacher had them hacking it, but they detected them, and now they're trying to prosecute them. And then they went back and tried to retroactively change the scope on the bug bounty program to say, well, you can only test like the sample data here, not the real data. And this is like what just happened like a week ago. I saw it. It didn't hit the news much because it got buried under all the other spectacular Trump nonsense. But last week, they contacted a bunch of Hillary Clinton's staff members to claim that they have now retroactively classified the stuff in the emails, so now they're prosecuting them for leaking classified emails, which were not classified at the time. And that's kind of mind-boggling too. But anyway,
they do that a lot of that.
I guess it's just a way to harass you, so you have to go to court with a lawyer and defend yourself. I can't believe that would really hold up in court.
There's something like constitutional, like you can't make stuff retroactively.
No, I don't think you can, but they can. Yeah, but they can force you to defend yourself, and that's an irritation. That's what they did to me. You can file bogus ethics complaints against anybody with a CISSP and force them to defend themselves, and that's what attrition did to me.
But I think with the intelligence agencies, they can prosecute with retroactive reclassifications. It happened to Hillary.
Wow.
Somebody recently too.
Well, that's pretty outrageous.
I mean, they never did prosecute her, but they could have.
Man. Well, that
is outrageous.
What's that? Yeah, I mean,
it is outrageous.
Yeah. The retroactive reclassification, that seems like that's got to be a violation of some amendment or other, but I'm not quite sure exactly where I understand. Anyway, so Kaspersky, I thought this is pretty exciting malware. What this malware does is it wants to break your TLS connections. Now that would be pretty spectacular. There have been other techniques to break TLS. One is, of course, you cannot brute force the TLS keys. Right? What you can do is you can forge certificates by compromising your certificate authority, and people have done that. Another thing you can do is capture the data before it's encrypted, but this is the first one with a new trick. What it does is it catches the RAM code for your browser. So when you make a TLS connection, your browser makes a local key, public-private key pair, and then it connects to the server like Google that has a public-private key pair, and then you encrypt the data. So that poisons the random number generator in your browser in RAM, so the numbers are not random. So it always produces a small key space of private keys, and now they can break in. That is pretty brilliant. And so it'd be fun to play with that and see how it goes. Maybe I'll get a copy of that and see if we can put in the malware analysis class maybe here. I found a bunch of real malware we could be analyzing here. I'm just a little nervous about handing out real malware to my students here. I might do something unwise with it. I wrote my own keylogger, and now I wrote my own ransomware. Got it working yesterday, so I'm not quite ready to hand it out yet, but I'll have it pretty soon. We'll probably have it next time I see you in 2 weeks. I'll have the homework where you analyze this ransomware. But I think, anyway, this is a pretty awesome trick. It's a good idea. I'd like to play with that. So this really caught my attention because this is very much what my thesis was. And I saw a popular press article about this that made it sound like it was duplicating what I did for my PhD. But what I did for my PhD was the first observation of molecular tunneling. And what we saw was that a carbon monoxide atom tunneled through an energy barrier, which has a quantum mechanical property that had never been observed in molecules. But these guys have a 25 kilodalton object, which is assemblies of 2,000 atoms. That's the size of a whole protein in a quantum uncertain state, which is, that is quite surprising. That's a very large object. That's certainly the largest object that has ever been put in an uncertain quantum state. And everyone wants to make it up to Schrodinger's cat. Schrodinger wanted to put a cat in a state that was both alive and dead at the same time. And we've never managed to have any large objects in these uncertain states, but that's a pretty large object in a quantum uncertain state. Dalton's is the weight of a proton. So it's 25,000 times the weight of a proton. So it's got a lot of atoms. Anyway, so this I thought was pretty interesting. They got a bunch of military generals to talk about Trump because Trump just pulled out of Syria. And I thought this was very interesting. They say, what's wrong with Trump? And these guys are willing to say it because they've retired. And they say the problem is he doesn't value expertise, which is certainly true. Trump is very much like say Chairman Mao, who said the experts are all just traitors and you shouldn't get rid of all the college professors and the books and everything, and people should cling to some other kind of knowledge like political truth instead of this rotten book learning that just makes people nasty elites. And he's very unstable too. It is the other. He only trusts his own instincts. He doesn't care what other people say, and he doesn't pay attention to security briefings, and he's briefed by Fox News, so he gets just crazy ideas and acts on them. So supposedly we're pulling out of Syria and leaving our allies to just get killed because Trump admitted years ago he has a conflict of interest because he has Trump towers in Turkey, and he's great friends with the dictator of Turkey. And Turkey wants to kill the Kurds, and Trump doesn't care, and he totally went along with that. But he did it in December. He did the same thing, just pull out and kill the Kurds, and the generals defied him and opposed him and talked him out of it. And now he fired all those guys, so now he's doing it again. But again, the generals have not actually implemented. I saw a tweet amazing 2 hours ago. I said, this troops did not leave Syria yet. Trump just went wild on Twitter, but we just ignored him and didn't leave Syria yet.
Can you reverse this decision?
He's done that before. And so, by the way, did Obama. Obama was going to go into Syria on the side of Assad because of chemical weapons, and they talked him out of it. The next day he said, oh, never mind, we won't do that. That's another thing generals hate. When you don't plan what you're going to say, then you say it, then you just change your mind and don't do it. This is considered a rotten way to run an army. But anyway, I think Trump does this all the time. Blow hard about something, and then when he gets pushed back, just blow the other way and pretend he never said it or something. So hopefully they can get him to just knock it off about Syria. We'll see. Anyway, this one was pretty interesting. This is the big thing now, DOE. DOE is DNS over HTTPS, so your DNS queries are encrypted. And a similar one is DNS over TLS, which is more or less the same thing. Some purists say it's a little mathematically better. Now, both of them, the original reason why everyone opposed this, and Paul Vixie, one of the guys real big in this, because DNS uses UDP to make it faster, to make it take less RAM on the server, less processing on the server. So one server can service more DNS requests. But these guys decided to just try it on a modern network, and they found that pages load faster over DOE than they do over UDP-based DNS. And I said, how can that be? HTTP has a handshake and everything. That's got to be slower. But it just turns out that the default timeout settings are 5 seconds for old-fashioned DNS over UDP because it's a really old protocol. And the timeout setting is more like half a second for DOE. So if the first request fails, the second request comes a lot sooner. So on networks where some of the packets get dropped, in fact, you get better results over DOE. So that the performance issue, at least from the viewpoint of the client, is non-existent. Now, in principle, the server has to work harder, but I bet it's not a big deal because I already went through a similar thing with Google went to HTTPS. Everyone said, oh, you can't go to HTTPS, it'll cost too much server CPU. And Google did it, and they said it's only 1% more server CPU. Because although, of course, it takes more calculation to send the data, it turns out that other things are most of the work anyway, and that little bit of added work doesn't matter. So anyway, we all seem to be going to this. The only people are all screaming now that this will block police surveillance and content filtering stuff because they've been doing it through DNS, which doesn't make any sense to me anyway, because this is back in the old days. 10 years ago, high school students would learn if you want to go to Facebook at school and they block Facebook, you just type in the IP address for Facebook and you go there because they were only blocking DNS. So I never thought DNS-based filtering was really any valuable thing anyway. But anyway, they're going to do it. Now, of course, another fair statement is that the privacy you get by encrypting your DNS request is complete garbage because everybody has to know what IP address you're going to anyway. You can't get the packets there without going to the IP address, so people can still tell where you're going by looking at the IP address. So you're kind of fooling yourself imagining that I can go to Facebook at work and nobody can tell because the DNS is encrypted. That's not really true. And besides, when I tested this about a year ago, I started sniffing in Wireshark and I switched to DNS or HTTPS and I still saw the domain names because when you do a TLS request, you send a SYN/SYN/ACK, and then it sends you the certificate. It has to send you the certificate before the encryption starts because you need the public key, and the certificate has the domain name in plain text in it. So the domain name of every site you go to is still sent in plain text over the wire, even with HTTPS. So you're kind of fooling yourself if you think that anything short of a real VPN is hiding your traffic. Now, if you have a real VPN set up correctly, which is only true for 20% of them, then all your data goes to the VPN server. It's encrypted all the way, the DNS requests and everything, and nobody can see that except your VPN provider. So that's what you should have if you want privacy, and all these halfway measures are a lot weaker. Anyway, yeah. Good, yeah.
What was the timeout between 2 seconds and half a second?
Yeah, 5 seconds, they said, for UDP-based DNS, and I think half a second for the modern one. So it's really not that the protocol is in principle faster, but the default installations of the newer one are faster.
So the old one, DNS over UDP?
Yeah, DNS over UDP was the original system. And of course, in principle, you could handle more millions of requests per second over UDP than you could over TCP. But in fact, on modern networks, it's probably not really true. Yeah.
So you want for privacy to hide your IPs, you want a VPN provider that has a lot of servers widely distributed?
Oh, I don't know. It depends on how you look at it. If it only had one server, then in principle, someone could issue them with a court order and find out what you were doing if they keep logs. But if they had one server and you're sure they don't keep logs, then it would be okay, I guess.
So, I mean, just to get across to your destination without.
Well, maybe having, well, I don't know, one reliable server might be better than, people usually want them all over because they want to change their location. Like appear to be, because they want to watch like shows that are only available in one location or something.
Right.
But yeah, and of course there's Tor, or maybe you want to hide your location, but that's the one. A VPN provider means that nobody can tell anything about your traffic except at the VPN server. All they see is you sending a bunch of data to the VPN server and nobody else. So nobody can even see the IP addresses or anything of where you're going, which is the point. All they know is the total amount of bytes you sent. They have no clue where it went. Anyway, so I think I'll skip these other ones and move on to the lecture because we're up to the time. So we're down to analyzing malicious Windows programs. And there's no class next week, a scheduling note, some kind of holiday, so we'll meet in 2 weeks. And there's a couple of projects up to keep you busy for next week or two. And I'll have new ones by the next time I see you for sure. I've already got some written. I'm just working on what to do with them. I found large repositories of malware. I'm hopefully I've already assigned some of it to other classes. I'm gonna try and choose malware that isn't too horrible. But anyway, of course, when you're analyzing malware, don't use it on a real laptop or a real machine here. Use a virtual machine or a cloud machine so we don't all get shut down and punished and everything. If you guys spread real malware around, I'll have to hear some unpleasant grumbling from committees and stuff. Maybe the FBI and stuff, yeah.
Does that happen this semester?
It has never happened to me at all. None of my students have ever got hacking anything or doing anything rotten, and I'd like to keep it that way. Now I have tenure, though.
Never actually hacked you.
As far as I can tell, no. Most of these because they're not dangerous enough, but in fact, I think the crooks don't go to school. But yeah, I was worried when I started. People were very afraid I was creating criminals and teaching students evil stuff, and that did not happen. I'd like to keep it that way. Here we go. I think the holiday is Monday, not Tuesday. I checked, it's Tuesday. It is not, there is a holiday on Monday, like Indigenous Peoples Day, but the college does not celebrate it. Tuesday, they have like faculty meetings and they canceled class for that. So I'm sure there is a political reason for this. There always is around here. But only that one day, just Tuesday, yeah. Yes, a lot of people are confused because there is apparently a federal holiday on Monday, but we're not honoring that one in the wisdom of the committees that decide these things, which is like the impenetrable wisdom of Trump. He said, in my infinite wisdom or something. He literally said that yesterday. So unmatched wisdom. So it sounds like a supervillain. Anyway, so all right. Let me just, in case anybody hadn't seen it, that should be here. This is the stuff. When I saw it, I literally thought it had to be the Onion or something. If I can figure out how to get my browser to operate, if I press, there it is, wisdom. Come on, stop messing with me. Come on. All right. And down here's the thing where I can put wisdom. There. There we are. Our fearless leader. In my great and unmatched wisdom, I will totally destroy and obliterate the economy of Turkey. Therefore, it is okay to pull out our troops and let the Kurds get killed because they will tremble before Trump's might and not do it, even though he authorized it, and they have in fact started bombing about 2 hours ago.
They did?
Yes, I saw it. They say they have. So the Assad forces have begun bombing the Kurds. The Turkey forces have started bombing the Kurds, which Trump gave them the green light for about 12 hours ago. In a personal phone call with the leader without telling anybody, he decided because he talked to the guy that's involved with his hotels and his best buddy, and he said, it's time, I want to bomb your allies. And he said, oh, sure, bomb my allies. I don't like those guys anyway. And that's where we are. But anyway, the generals and soldiers are all scrambling around trying to undo this, and they may succeed. Anyway, so if you do anything in Windows, you do it through the API. The API is the application program interface, and this is how you do everything in Windows, just saying how you do everything on Facebook. They give you a platform, and your application developers are living on the platform, and if you want to open a window, you ask the operating system, please open the window. If you want to read the keyboard, you ask the operating system, please read the keyboard and tell me what it says and all that. That's how you do it. So here's how it works. It has its own names to represent C types, such as DWord and Word. It uses Hungarian notation. So it uses letters before integer variables. So DW is a double word, 32-bit, unsigned, and so on. So you got word, double word, handles, and long pointer. You have these prefixes for variable types and for functions that tell you what type of data they expect. And then you have handles, which you talked about before. If you're in C and you want to write to a file, first you do f equals open file name, and now you have a handle called f, and you do f.write, f.close to refer to it. And those handles are objects in memory that refer to other objects, and you have a lot of handles in every program while it's running. So all handles are is pointers to objects you're working with. And so if you do create window, there's originally some create window function. In modern versions of Windows, it's the create window extended function. This is a very common thing you see in Microsoft, put EX at the end. And so you call create window EX with some parameters like whether the window should have a scroll bar and whether it should be on top and things like that. And if you should, then you will get return value, which is the handle to that window. So you set H equals create window, and then later on you can do H close, H maximize, H focus, and all this jazz. So that's the game. So you can create a file, read a file, write a file, and create a file mapping used by malware. These will load files into RAM, so you can execute a file manually instead of using a Windows loader. And this is a powerful technique to sneak malware onto a system. And I wrote a bunch of projects doing it with Python years ago, where you may create a data object that contains executable code. You load the program, you load it in memory, and then you execute that data object as code. And there was an example of that in the exploit development class. This is how you can test shellcode. You can put it in a C array and then jump to it as if it was a function. Yeah.
Can you do that with a debugger?
Yes, you can certainly do that with a debugger. You can just have it loaded in the data section. You can just move the EIP down to there and run it. Yeah. Yeah. So there are special files. This is a Microsoft notation. You can do a \\\, which is the root of the whole system, like the Linux /, and then you can refer to like a name of a server and the name of a share to get a shared SMB server on a Microsoft LAN. Or you can put this question mark here, which will disable string parsing, so you can have longer file names. One important thing to realize about Windows is that it never stopped using the DOS 8.3 file names. If you're old enough, you'll remember back in the old days, you could have 8 characters in the file name and then a dot and 3 more characters, and that was it. And so if you have a file with a name like my documents, there's a second name for that file. The way Microsoft stores names that are longer than 8 characters is it stores the first 8 characters in one 8.3 file, and then it has a series of further file names and pointers to extend it. And so this is actually stored. Another way to refer to this object is there's a thing like this, and I think there's a special character in front of it, but the point is there is actually an 8-character name for every object. And there are certain conditions where you can do MS-DOS command line commands and you reveal this. If you do something like to refer to groups of files with asterisks, you often get unexpected results because the real file name is still the 8.3 file name. The long file name is like metadata that is only used to show it to you. It's not really the file name that the operating system uses to refer to things. And so there are these special file names that go all the way back to MS-DOS. And so you got like, this is the / of the whole thing. This is the device namespace, like /dev in Linux that refers to direct I/O to hardware. You can do direct writing to hardware in Linux, in Windows. And so this wrote to the physical disk to corrupt the disk, / physical disk 1. That is direct disk I/O, as opposed to disk I/O by volumes like C, D, and E, which are partitions on a disk intended to be used by the operating system. You can also write directly to disk. And if you do forensics, this is a big deal. If you do forensic of active files, then you go to the volumes, but you can also do a copy of the entire disk at the root level where it does not matter what file system is on it. You just copy every byte off the disk with this kind of notation. Anyway, and then there's alternate data streams. This is an old trick. This is actually a Microsoft trick to be compatible with Apple, which is something you don't hear that often. So what happened is Apple was the first computer that really got into media. So they wanted you to play like albums. And so they wanted to have a stream of music to a file name, but then they wanted to also have liner notes and cover art tied to the same handle. So you can have alternate data streams tied to the same file name. And so you can do that in Windows. And what you do is you can echo data like this one in the middle, echo 2222 to foo:\bar. You can echo After you create a file, you can then echo into file name : another file name, where you treat the file as if it was a drive. And you can put more data attached to the same file.
You
So
do that with DOS.
you can do that with DOS. It's been supported for a long time. And until there was a time like around 2000 when antivirus products were not onto this, and malware could hide in the alternate data streams and the virus tools would not scan in there. That's not been true for a long time. They have caught on to this. But it is one of the many strange places to hide data where it's hard to see them. And you don't see them if you do dir. There is a dir/p command or something that will find it now in modern versions of Windows. But there's a time when you actually had to download a special program called LADS to list the alternate data streams, because although it works, they're not easy to find. Anyway, but those are some of the special files. And of course, a big issue is the Windows registry. This is where you spend a lot of time in most forensic classes. The Windows registry is really quite confusing, and you have to get used to it. This is a Microsoft invention. You'll find nothing like it on Linux. In the original, MS-DOS was like Linux. If you installed a program, it would just have its own configuration file, which would be a text file. And back then, you typically just have C like Firefox or Firefox, and C like word for word. You put everything in there, and there'd be word configurations files in there. And that's what this still is in Linux. But in Windows, for some reason, in Windows 95, they decided that this was too disorganized and messed up, and they were going to take all the configuration files for everything and sweep it into one database, a binary database, and that's what the registry is. The registry is all the parameters for all the settings, for all the Windows features, and all the installed software in one big tree structuring directory. And you can do all sorts of surprising things in the registry, like you can make things automatically start, and that's what you see for what we're going to do here. We'll be seeing persistent mechanisms through the registry. It's one of the many auto-start extensibility points. There are about 40 of them, and there's a tool called auto-runs from, let me bring that up. That's actually worth making a note about auto-runs. If you haven't seen this one, this is an awesome tool. Autoruns is another tool from Mark Rusinovich. What this does is it finds out all the things that are automatically starting on your Windows machine. And there are a lot more than you would think, and there are about 30 or 40 ways to make things automatically start. And this is the only tool I know that comes close to finding them all. There's many registry keys, there's startup folders, there's many, many other ways. There's scheduled tasks. There's many different ways to make something automatically start, and this will find them all and print them out so you can see them. So anyway, malware, of course, is in the business of making it automatically restart every time you reboot your machine, and using the most obscure way to accomplish that so you can't find like a shortcut in the startup folder or anything and easily delete it. So here's the basics of the registry. There are 5 root keys. These things that look like folders are for some reason called keys. They act a lot like folders. The only one thing that's different between these things and folders is they can never be empty. If you go to HKey current, even if there's nothing in the key, it will always have one object called default with the value not set. That gives you a clue that this is actually something like a database record. It is not like a folder. Anyway, but it looks like a folder, and every Windows machine has these 5 folders at the bottom. This is a more messed up database than you could ever imagine. There are not, these 5 objects are stored as, I think, 13 files on the disk, and they're not even independent. Some of these are actually just subsets of the others. This is the way Microsoft always is. Unix is like logical and clean, and Microsoft is always just a snarled up mess, because they only think about having a business function the way a business person wants it. And if there's another business function that does almost the same thing, they just have another name to do almost the same thing. That's why there's like 10 different ways to do everything on Windows, and it bothers you if you're into logic. But anyway, so HKey class is root, current user, local machine, users, and current config. Those are the root hives. So those things have subkeys. So here's the basic ones. A local machine is on the local machine. This is the current user. Here are all the users. So HKey current user actually points to something inside HKey users and so on. It is like pretty messed up, very far from there being 5 objects, but that's the game. Anyway, if you take a forensics class, you go through maybe a couple of dozen of these things that are real important for forensics, like setting the time zone and listing all the USB devices that have been connected and such. But the ones most important to us are the persistence ones, and the simplest persistent ones are the run keys. There's 4 or 6 of these ways to make something automatically run. In HKey, local machine, software, Microsoft Windows current version, run. So here's one on one of my machines showing various objects running, like LogMeIn and Adobe ARM and so on. Many programs you install put a key here, and then you just see there's a string value with the path to the thing to launch every time you reboot. This is one of the many ways to automatically launch things. So there's the sysinternals tool that will find all these things. There are many, many other ways to load things, registry locations and many other objects. So that's auto runs in all its glory. And so here's some registry functions. You can reg open key X is the API call to open a registry key. So you can edit it here, setting a value, getting a value, and so on. And documentation will often not include the trailing W or A because the documentation is telling you what parameters go in and such, and it doesn't really matter. But it's a thing to know. Your call might actually have a W or the A at the end, which will not be present in all the documentation, just to make sure you stay confused. So here's an explanation of this stuff. X is something extended. When they update it, you might even see XX. A is for ASCII, and W is for wide words. So that's the game there. So here's code that modifies registry settings in assembly code. So here it's going to push parameters onto the stack, and then it's going to call reg open key. So here, remember this is the way it always looks in assembly. You have a call, and before that you have push, 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 putting all the parameters on a stack. So this is up one parameter, two, here's the options, here's the sub key. This is where you put in the path to the key, software, Microsoft, Windows, and all that jazz. Here's the home key. So it's a sub key of this primary key. Those are in two separate parameters for some reason. And then you call this thing, now it opens the key. Now you check to see if the return value is 0. 0 usually means, and then you jump, if it's not 0, down to 28C5, which I guess is off the screen. And I think this is what you do otherwise. Now you're going to write the data. So you're going to reg set value. So apparently 0 means that it failed. This is pretty common for things that return a handle. A return of 0 means I was not able to open that key. But if it is not 0, then you have a valid key, and now you can set the value. And the value EAX that came in is going to be pushed onto the stack someplace like here. Probably a little more complicated than that. I think this mess is what does it. But you're going to have to put the handle pointing to the thing you just opened into the next call. This set value, one of the parameters will be a handle to the registry key you just opened. So this whole mess is one API call. Push, 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 pushing what look like 8 or 10 parameters on the stack and then calling it. So this is 2 lines of C++. This is one reg call and one more reg call. And in here is an if to see if the result was 0. So that's 3 lines of C basically that you're seeing here. And so you can also save reg files. If you want to save a registry condition, and the most common situation with this is you want to do something like block a Windows update. So you want to change one registry key. Now, you will learn if you do Windows tech support, you never tell end users to open regedit and change something. You'll be sorry because they'll change the wrong thing, crash your machine and your host. So if you do want to push out a registry change to your users, you want to somehow automate it. And the simplest way to automate it is reg files. You can go into any subkey and right-click and save a reg file just from this and its subkeys. You can also save the whole registry in a reg file, at least one whole root high if you want to, but normally you save one reg file, and the reg file is just a simple text object. Registry editor, and then it's just a nice, simple, readable list. This is that object. So you could save a reg file, and if people double-click on a reg file, it'll put those values in the registry. So this is one simple way to distribute registry changes to end users if you don't want to bother writing a compilable program. Yeah. Of course, but that's true of every update. This is why one of the crazy things about security is if you want to put malware on a machine, just put up like a fake Adobe update. Here, download this file. Please elevate to administrator. Please install it. Thanks. People will just do it, and often they'll automatically do it, and that's why it's kind of nuts. And that's why I say try to sign this stuff and hopefully get it from the right server, and there are many, many cases where that failed. And there's a module in Kali that will put up fake updates. Doesn't seem to be updated enough to work too well on modern systems, but it's a pretty awesome idea. And most people know this. You open a page, it says you have to put on a flash update or something. It's probably one of the primary ways. That's a problem. And that's, fundamentally, you get code from people all the time and you run it without really knowing it's okay. That's the problem. Anyway, we got some Cahoots. Let's see how they look. I should have them open someplace. Here we are. So I got 7A. Look good. And I have a page here to put some stuff in. Good. That doesn't seem to be launching. I thought I hit something. There it goes. All right. This is why I always thought whitelisting would be the thing. Your administrator ought to have a list of all the things you're allowed to run, and you're not allowed to run anything else. And in principle, you'd be a lot safer, but in practice, it's too much bother to keep that list updated.
Someone's closing this curve, and that's not me.
What's that?
Someone's closing this curve, but that's not
Someone's posing, well, that's true. We have, that's one issue, imposters in Kahoot. It's like people going and confessing to a crime. You know, it's like, that, I used to have a guy that lived with me, always asking me these questions. He said, what would you do if a student came and demanded a lower grade? And I said, well, that will never happen. And then it happened. I mean, you do this long enough, every exception will come in. Well, we might dump Trump. We'll see. A lot of people are mad at him, but they were mad at him from the start. But I don't know. It's beginning to look like we might be able to get rid of him. Who knows? Who's advertising? Oh, well, I know in the Silicon Valley, he has a lot of supporters because they want the tax cuts. In San Francisco, I think not so much. But who? Carminetti? Scott Malini. I don't think I know him. Yeah. Okay. Microsystem. Yeah, I think a lot of big, a lot of big companies, they want him. So let's see, this is Kahoot.
Julie Brown said, call me crazy, but I'd say Hillary's got a chance against Trump.
Say Hillary's what?
Hillary's got a great chance, the best chance of beating him.
Oh,
again?
She's got the brains, brawn.
Well, I don't think she wants to do it, but yeah. Well, I know. At first, I thought they should run her just because they got no credibility to lose with her, and since there's no hope in hell, they might as well not throw a good candidate away against him. But I don't think any of that's so true anymore. I think he's looking vulnerable lately, a lot more vulnerable than he was a month ago. A month ago, I thought they didn't have any chance at all. Anyway, so things change fast, and a lot of people have said, you know, don't rule out people like Buttigieg and Klobuchar and stuff, because at this time in 2015, Trump is at 1%, and everybody thought he had no chance of getting a nomination. So one of those people from the bottom of the Democrats might crawl to the top. We'll see what happens. Anyway, we'll see. So a pointer to an object. I know some people think Yang is the guy, and he's risen up a lot and he made it to the election. I don't know.
Everybody wants money.
Yeah. So the second stream of data in a file. Okay, that's alternate data streams. A root key. Okay, that's each key current user. Good. All right. And assist internals tool. That's auto runs. All right, good. And a pointer to an object. Didn't we already do this one?
I
Yeah,
think so, yeah.
I'm going to skip this one. All right. Someone fouled it up. Or write these questions should be fired. Anyway, so, all right. So I got Dump Trump will have to tell me who they are. Vin and Rich look like real names, though. So Dump will have to come out of the closet or they won't get their points. Aha! Here comes a chat message. Aha! Okay, good. I have discovered it's Ed. Okay, good. All right. All right, good. So let's go to the slides, do some more of this. So the networking APIs. All right, so these use the Berkeley compatible sockets. There are two kinds of networking APIs in Windows. There are high-level APIs like Internet Open URL, which do a big network activity in one call, and that is what most people would use. But they do have direct sockets if you want them, and those are the Berkeley compatible sockets, and these are based on BSD Unix, which defined the internet and had the basic concept of TCP sockets from the very beginning, and they're the same in Python and Linux and Windows because they're all straight from the original plan here. And that's what WS232.dil contains. And so it is the same stuff that you'll see, same thing I've been doing in Python for years. Bind listens, attaches a process to a socket, a port so it can receive data. Socket creates a socket object. Then you can listen and accept data, or you can be the client and connect to a server, and then you can send and receive to the server. So these are the fundamental functions that are the same in every language. They're at the heart of the internet. And so on the server side, you see these calls in order. First, you create a socket object, then you bind to a port, then you listen and accept data. Then after that, you'll have send and receive. You accept a connection. On the client side, it's create a socket object, then connect to the server, and then send and receive. Those are the patterns you'll see if you do these things. And if you use a high-level API call, like Internet Open URL, it does all this for you automatically. So here's a simple server program. You would call startup for WSA, and then you would call socket to create the socket, bind to bind it to a port, listen to listen, and then accept a connection. So you see these API calls go by. And then, of course, you would also, in proper code, you should be calling error all the time. Every time you do something, you should stop and see if there's an error, do something. If there's an error, do something else. That's why, real programmers have to spend most of their time handling exceptions and errors. Sleazy people writing things like shellcode and malware can afford to just ignore all that. Or hackers writing pen testing tools where they don't really need it to work under normal conditions. And a lot of people, machines, they just want it to work once on my machine. All right. So the WinINet API is the higher level one I was talking about, which is what a normal programmer would use. No normal person would write code using WS232. You'd have to be nuts. Why would you want to do your own TCP handshake? You just want to call something high level like Internet Open to connect Internet Open URL, Internet Read File. That's what you want. And it will then call all those other lower level functions itself in some pattern to make it work. So this is what a normal person would use WinINet. And this, I think, is, all right. This other stuff is the WinShock library, but this is the higher level stuff, WinINet. All right, so if you want to follow running malware, you can do jump and call at the assembly language level to run other code in your same program, but there's a lot of other ways to run code in another program, and this is, of course, what makes Windows powerful and what makes it vulnerable. You can run code that's in a library. You can run code in different processes, and you can use mutexes and COM objects and so on. These are all ways to mix other code outside of your process with other processes. And that's, of course, a powerful technique, but it can get kind of weird. So DILs are the main thing. The whole point of DILs is to make Microsoft faster and more efficient. So if one bit of code uses something like WinINet because it's doing networking, if you open another networking application, it just uses the same copy of WinINet already loaded in RAM. You don't have to wait for another disk read. You don't have to use more RAM. They just share the same library. So that's dynamically linked libraries. At runtime, it finds out where that library is and connects you to it. So DIL's export handles code. There are entry points for every function that comes in, and you can call the same library at many different locations to get the different functions out of it. Now, there are static libraries, which are commonly used in Linux, but not in Windows, where you actually make a separate copy of the library for every program you compile, and the program is big. Every program has its own copy of all the libraries. So each program is more independent, but now it's more wasteful. If you have several programs running at once, they're making multiple copies of things, and then they can't share memory among running processes, which is sort of more secure and sanitary, but it's not how Microsoft does it. Of course, to be fair, in the Linux world, you might be thinking about something like a little home router or something where it's really not going to be running many processes and it's not really a general purpose device, whereas a Windows machine is supposed to have a user and they're opening browsers and email and chat messages, and you expect them to be running many, many things at the same time, whereas servers, you pretty much run just one or two things and you want them to run really fast. So it's a different philosophy. Anyway, that's the game. This makes code smaller, and it also means you can buy DILs from people, buy libraries from people and other code and put them together. And so when you get a program, it typically has not just an exe anymore, DILs come along with it. And these days it comes with an installer file that installs all sorts of stuff. So you can put malicious code in a DIL, and you can sometimes trick other processes into loading that DIL. You can use existing Windows DILs, and you can use third-party DILs. These are all ways to use libraries to do malicious things. So DILs are like EXEs. They are portable executable files. They have a header and so on. There's a flag in the header that tells it that it's a library and not an EXE. It has, of course, many exports because those are all the ways to enter it. And every time you load a DIL, it immediately runs DIL main to prepare the DIL. So for malicious DILs, you often put the malware in DIL main, and now you don't actually have to call anything from the victim EXE. You just need to load the DIL, and that's enough to run your malware. Yeah.
What was it, the DIL in the old Windows? Was it autoexec.batch or?
Autoexec.bat was, and win.ini, but there were always DILs. I know back to Windows 98 there were, because I know when you would install software, it would often say, I'm missing x4739.dil. And when you, so it had DILs back in Windows 98, I'm not sure about MS-DOS. MS-DOS might not have had them, I'm not sure, because MS-DOS was a single process machine. You could not run two processes at the same time. So it didn't have this issue. I think this was Windows 95 or Windows 98 that it came out. Might have been in Windows 3.1 though. I'm not sure. I wasn't that aware of the details back then. But I know it was there by Windows 98 because Windows 98 had DIL help, where programs would stop running because you had uninstalled a different program and that had removed the DILs you need. Because Microsoft never learned how to keep track of how many programs are relying on a DIL, so they know when it's time to delete it. They haven't solved that problem yet, although Linux solved it in around 1980.
Both 95 and 98. I'm not sure on 3.1.
Yeah, 95 had DILs too. Yeah, good.
No, the issue.
Oh, well, if that issue was there, then they had DILs. Yeah. Anyway, so every program you run is a process, and each process has its own memory allocations and its own handles, and then it has threads. So older malware, back in the days of say MS Blast, you would just open Task Manager and you could see the malware running as a separate process and terminate it. So that's kind of cheap and easy nowadays to execute code by hiding it in another process. So if you go to the Task Manager, you'll see all the processes running on your machine. You got like Notepad and Explorer drawing your desktop and everything else. All these, and you can kill them one by one here, although some of them are essential, and if you kill them, you kill the machine. So each process has its own resources and its own memory, and they all think they're running at the same virtual address of 400,000, but they're in fact all running at different real physical address spaces. So you can call the create process API to spawn a new process, and you have a startup info parameter here, which can make a listening socket over the network, or it can connect to the standard output. So you can launch a process that takes its input from a keyboard, or launch a process that takes its input from a network connection. So clearly this call could be used to create a remote shell, where commands received over the network are executed. So here's the code to do it. You prepare a socket handle, and now you move a bunch of stuff into locations on the stack. Instead of using push, it's moving it ESP plus something. So you put a series of values up on the stack, and then you call a, I think it might be on the next page, yeah, where you call create process. So you're just setting up all the parameters and putting them all on the stack, and that will create the process. So here it loads the socket handle, standard error output, and standard input. Those are some of the parameters, and now it's a command line to be executed, and then when the create process is called, it executes that command line to create the process, and that will refer to some kind of runnable executable. So this is basically what happens if you go into start run and type in the name of something and press enter. This is what will be happening to launch that process.
Could you back up one page, please?
Yeah,
Question
yeah.
on that.
Yeah.
You know, there's 1, 2, 3, 4.
Yeah,
Aren't they all moving
the same
X
thing.
into the same memory location?
No, it's moved this into that. They're putting the same value in several of these things because this is standard error, standard output, and standard input. So I think those are all just default values. Yeah. All right. So you got threads. The processes are containers, and it's broken up into one or more threads, which are the units that actually get CPU time. So that's the point. These are independent sequences of instructions, and the point is if one thread is waiting for something slow, like user input, other parts of the program can keep going by putting them in a different thread. So this thread runs in a certain context. It has complete control of the CPU while it's running. So when you are allocating CPU time to one thread, you have to stop running the other thread, preserve your state, move the thread context to this thread so it can move forward. And then when it's time to go to the next one, you have to switch the thread context again. So that's the game there. So create thread. We'll start a thread, and this gives you a start address. And so one thing you can do is load a malicious DIL into a process with create thread. Create 2 threads, 1 for input and 1 for output. And now you can send data into and out of your malicious code. Mutexes, we mentioned before, mutexes are handles which are visible to other processes. So they are marks you can put that can be detected in memory by other processes, and they're something you would do for something like record locking. I used to do database administration, so someone would open a database record, start changing someone's address, and if someone else tried to open the same record and change the same record at the same time, they would get a message, that record is locked. There's a record saying you can't open that and modify it until somebody else is done modifying it, and that's the kind of thing you do with a handle. So in user land, you call them mutexes. In the kernel, you call them mutants. I don't know why, but they both serve the same purpose. They are handles that are visible to multiple processes, so you can send a signal to other processes on the machine, telling them something they should know. And so in malware, typically it is a mark to indicate this machine is infected. So you can wait for a single object. This will give a thread access to mutex, then release mutex, create mutex, open mutex. These are the API calls to create and read mutex. So you'll find in your malware that it checks to see if a mutex exists, and I think we got that here. So here it's going to do open mutex, and here it's going to create mutex. So this is the code that first looks to see, is this box already infected? Because the mutex is there, and if not, then I'm about to infect it, so create that mutex. And here's the name of it, HGL345, which is probably intended to look something like a graphics card driver or something. So it makes this mark, and now you've got an indicator of compromise. That'll be in the infected boxes, they will have that mutex. That's what the malware itself uses to tell if it's already infected. So I got cahoots about that. Yeah, let's see if I can get to them. That's 7B. So it's here. Okay. Iron Man. All right, I'll give it a few more seconds, but I think 8 may be all we have. All right. So bind and accept, where are they? WS2, the old one. WinShock. They call this the WinShock software. All right. Internet read file. Okay, that's WinINet, the new higher level one, more fun than WinShock. All right, a type of file differing from an exe by one flag value. Those are the DILs, good. Dynamically linked libraries. And a global object used to coordinate multiple processes. All right, that's a mutex. That's the flag where one process makes a mark that another process can read. So I see Vin again, and Rich again, and Ken. All right. All right. Well, it's 5 minutes to 6. Let's take a 10-minute break. We'll pick up at 5 after 7. I'm going to pause the recording. I'll leave the share going. Resume this. All right. So services run in the background, and they provide a service to many applications. So they're doing things like Microsoft internal services and so on. There's a lot of these, and they launch typically before you log in. So they typically have to run as system. And you'll see them in groups here: local services, app hosts, network services, and so on. And they often run as SVC host as far as a process. One SV host process will run several services, and you can see them more easily in Process Explorer. So like I say, they often run as system, which they have to, because they have to launch before you even log in. Like WinLogon is this process that runs, shows you the login prompt, and that clearly has to launch before you log in, so it has to run a system. And so they often automatically launch every time you reboot the machine. Microsoft Windows has something like 50 or more of these that run every time Windows is running. And so that's already a built-in persistence mechanism. During the process of boot up, it launches all these services. So some malware also launches as system every time you boot up. And so here are the service API functions. This will return a handle to the Service Control Manager, SCM. This will create a service, and this will start a service. You can do all these things with command line commands starting with SC, or you can do them with API calls in any software you want. And there is a, this is the type of service used by malware. This is a shared process. This stores code for the service in a DIL, and this is the one that runs in SVC host. That's where you'll typically find it. And so here's SVC host in Process Explorer. You see a whole bunch of instances of SVC host. And if you hover along them, it'll show you the command line, which showed how it was launched. This has access to the local system, network restricted, and it's running the network connections and offline files and remote desktops and superfetch. So each one of these is running a bunch of internal Windows services. And if you were infected, it would add another one to this list and be running some kind of malware at the same time. So there's also things that run as an exe in an independent process, and things that load in the kernel, other kinds of services you can have. We'll hear about this more, and we'll be looking in the kernel more as we go ahead. We'll be doing some kernel debugging, and you'll see kernel drivers. All drivers for all hardware have to be in the kernel, and you can make malicious hardware drivers that go in the kernel and do malicious things like keylogging. The services are in the registry. You can go down here to HKey local machine, current control set, services, browser, this whole mess, and you'll see information about the services here. So there are start values. Here's a start value down here. The start value is 3, and here's the choices. 3 is load on demand, and there are other things like load automatically. You'll see them in the task manager and in the services control panel when your services are going to load. So here's the SC command. In Windows, you can do SC, and you can query about the service and get information about it. You can also create services, launch services, start services, restart services, stop them, and so on from the command line with SC. Now, another object floating around is component object model objects. COM objects are used. That's another way, sort of like a DIL, for code to be running, which can be referred to elsewhere. And so These you must use OLE initialize or co-initialize. OLE is object linking and embedding, and it's used to put multimedia objects in Microsoft Word documents, but it's a more general process that can be used to mix processes together in Windows. So you have these COM libraries, and they're accessed by these globally unique identifiers, GUIDs. There are class identifiers and interface identifiers. And these are all terms you see if you go through Windows. There's one thing that came out about 5 years ago in the end, toward the end of Windows XP. They said God mode. There was this GUID you could run that gave you a master control panel of everything on Windows. It was sort of like control panel. And you can launch every Windows object by doing start run and a GUID. There's a GUID for the desktop and the documents folder and everything. That's what really happens. Anyway, so you can have exceptions, which we talked about before, and we'll be playing with more in the future as we do exploits against Windows software in the exploit development class. And here we'll see it from the other side. But anyway, you have exceptions. If you have a divide by zero or an attempt to run memory code in a non-executable part of memory, or an attempt to access kernel space from user land or any of a variety of other things, then you have an exception. The exceptions are then passed to the structured exception handler, which is part of the current program. And the current program has an option to handle the exception. The person who writes the program, like I mentioned before, a professional programmer spends most of their time handling exceptions. You make a program that does something, and then you make sure you've thought of everything that could go wrong, and you do something controlled and logical about all those things that might go wrong. And so you also consider serious exceptions, and you might write something in your code that will handle that. So it'll pop up some box under your control saying, we have a problem, please call our tech support, this number or something. If you don't handle it, it'll get passed back to the operating system. Then it's an unhandled exception, and it'll lead to something like a Windows-generated automatic message like this program has crashed, or please tell Microsoft about this problem, or a blue screen of death. So FS is :0. The FS is a segment register in the processor, and that stores the location of the exception register. So you can do that. There are 6 segment registers, so it's easy to find the exception handler, especially in earlier versions of Windows, and that was a common place to put attack code, put pointers to attack code, because it's a place you could easily find. Anyway, and then of course there's the big issue of kernel versus user mode, which will come back to us a lot. So the hardware on the motherboard enforces 4 rings of security. There's ring 0, which is kernel mode, which is the only mode in which the processor can run all of its assembly language instructions. The processor is built with something like 10,000 machine language instructions in the hardware, but you have to be running in ring 0 mode to have access to them. If you're running in some other mode, then there are certain commands you are not allowed to use, which will cause an exception if you try to use them, because you're not authorized. Now, for some reason, the hardware supports 4 rings, but nobody uses them. No modern operating system ever uses anything but ring 0 and ring 3. And now, by the way, they use ring -1, which is hardware-supported virtualization, which lets you support a second kernel and participates with virtual machines to make them run fast. But that's a little mind-bending and off the chart. But this is something you should be used to from the world of networking. You define like switches and routers and MAC addresses and IP addresses, and then you got VLANs that just break the rules and all kinds of other things. As soon as you have any list of options, somebody will make hardware that adds another option. And that's just the way it always is. Nothing is ever quite as clean as in theory here. But anyway, that's the game. Ring 3 is user mode, ring 0 is kernel mode. Everything you launch after you log in is user mode. It's launched with your privileges, and you launch it from the start button or the command line or anything. That's all user mode code. And the purpose of all this is supposedly everything you run is run in a nice sandbox where you can run code and you can like run out of memory, but none of your code can crash the machine. That's the idea. You can't kill the whole computer. All you can do is have your app crash and it won't affect the other apps. That's the idea. That's the goal of all this, to protect the operating system from your buggy code. It's not perfect, but in general it works. So if the code you're running wants to use the hardware, it has to go through the Windows API. If it does not directly execute kernel functions, it just uses the kernel functions through the Microsoft written code, which is hopefully better than the garbage you're running in user land. So each process has its own memory, its own permissions, its own resources. If it executes an invalid instruction and crashes, then Microsoft doesn't crash the whole OS. It will just pop up a box saying, this one app has crashed, shall I restart it or something? And it can do that because the kernel is still running without being corrupted. If you want to call the kernel, then you have to use instructions like this, sysenter, syscall, or int2e, are things which will then call specific kernel mode calls. And there are charts of these. So there are kernel processes. Now the kernel does not have this separation of processes, which is something that blew my mind. About 8 years ago with Kirk, I started researching IPv6 maybe 10 years ago, and we found an IPv6 attack that would crash Windows machines with a blue screen of death. And I started demonstrating at conventions. I did it at DEF CON, and I asked, how can this be that it crashes a Windows machine? You had to send these IPv6 packets, and if you send a few of them, it's fine. But if you send too many too fast, the whole thing dies with the blue screen of death. And I asked people, they said, why don't you debug the kernel and find out why that happened? I said, well, I don't know how to do that. Now I know how to do that, but at the time I didn't know how to do that. And I said, how can it be? And they said, well, that's not really an interesting attack. That's just a resource exhaustion attack. And I say, how can it be that I can exhaust resources in the kernel? And don't kernel, if I launch a program on the desktop, it'll tell me, I'm sorry, there's not enough memory to launch this program. Knock it off. Doesn't that happen in the kernel? And they said, no, it doesn't. And I said, you gotta be lying to me. That can't be true. Kernel processes don't bother to check and see if there are enough resources. They just load it, and if it's wrong, the whole thing crashes. They say, yes, that's really how it works, because we want it to be fast as possible, so we totally don't bother. And I said, no, that can't be right. And it's right. This is really true. It doesn't have the segmentation and virtual memory. It's all designed for speed, I think. So anyway, it's kind of mind-boggling. So if one kernel process starts using up too much RAM, the whole thing just dies with a blue screen of death.
There's no way to cross-check or anything?
Well, it's a good question. It's not typically done for some reason. And I asked people, the same thing is apparently true of Android phones. You can launch a process, because they kill Android phones, the same attack. You can launch a process, and if it doesn't have enough RAM, they'll just crash the phone. It doesn't have a way. I said, isn't there some way for it to query, is there enough RAM before I launch this? And they said, no, there isn't. This is also hard for me to believe, but it's apparently really true of the kernel anyway. Anyway, this is why if somebody had a real CS degree, which I don't, maybe they would be familiar with this stuff. I know Tom was that way. Tom was a real software developer. He had like a master's or PhD in software engineering. Then he started learning security. He was awesome at it because he knew all this stuff that I'm only kind of guessing at. He really understood exactly how the computer works. And when it occurred to him to do security, he was able to zip right ahead through this stuff. Anyway, that's the game. It certainly is true. If the kernel, if anything goes wrong in the kernel, you get the blue screen of death. There is no way for it to pop up a message and recover from it, because there's nothing still working underneath it to pop up that message. It just gives you the blue screen of death and dies on you. And now the problem is, if you want to have any security software, it has to run in kernel mode. Because if you think about what it does, you put in a floppy disk, you double click on a program, the operating system says, okay, time to launch that program. Your antivirus says, wait, before you launch that program, I have to scan it. Now, how can it do that? It has to hook the double click. It has to do it in kernel mode. And so you have to have device drivers in the kernel for your antivirus, so the kernel has code written by McAfee. Microsoft really, really does not like this, because they found out in Windows XP, they added the Windows Genuine Advantage, and they added this box that would report to Microsoft every time your machine crashed. And they found that like 70 or 80% of all the blue screens of death are caused by non-Microsoft code in the kernel. Crappy device drivers. Because if you make like a network card, and you're too sloppy to like read all the Microsoft latest white papers and bring all your code up to specs, you can just take the driver you wrote for Windows 98 and change a letter in the text mode part of the driver. There's a config file. You say, oh, this driver's fine for Windows 10. Just use it on Windows 10 and not bother to update the driver, which is what a lot of them do. And in fact, Microsoft supports a lot of legacy calls and stuff, so most of the time it will actually work, but of course it's going to have bugs. So if you buy cheap, crappy hardware, it comes with cheap, crappy drivers, which corrupts your kernel with junk and causes a blue screen of death. And Microsoft is very, very, very annoyed by this, because they get blamed for it. Windows sucks, it gave you the blue screen of death. So they make it harder and harder to do this. They tried to block them all out completely in Vista. They tried to enforce signing of the entire kernel, which is what iPads have and iPhones. The entire kernel is signed by Apple. When it boots up, it verifies the digital certificate with Apple to say this is a genuine kernel that has not been modified even by 1 bit from the original Apple thing, and that it will not boot up unless that is true. And Microsoft wanted to do that to Windows, but McAfee and Norton sued and said, we're going to give an antitrust lawsuit if you do that, because that will end our entire business model. And they didn't. Now, I think some Windows 10 tablets are now finally doing this. If you buy Microsoft Surface tablets or something, some of them say they'll have this signature enforcement of the kernel, which means it has to be 100% Microsoft software all the way through. You can have user land software from another company, but you can't have kernel software from anybody but Microsoft, so it's signed by them. And that would end kernel mode rootkits. But anyway, that's why you don't have kernel mode rootkits on iOS, as far as I know. There's no easy way to get them in. That's why iPhones are essentially your most perfect computing platform. For all practical purposes, your iPhones have no security products and no malware. No firewall, no antivirus, no nothing. You can't put it on. You don't need it because there's no way to get malware on it. Now, the NSA can do it, and a few advanced resistant threat actors can do it, but normal criminals cannot get malware on your iPhone. You just don't have to worry about it because you can only get code from the store, and they won't let you put malware in the store. Android, that is manifestly not true. So anyway, you can put malware in the kernel mode on Windows machines because they don't have that signature enforcement. So you can modify it, and every time you install hardware, you have to install a kernel driver for your printer and your NIC and everything, and that's all written by random third-party companies. So everybody does just add more code to the kernel routinely during installations, and therefore you can put malware in the kernel. And those are kernel mode rootkits, and those are the most dangerous, most difficult rootkits to detect and remove. That's the game. And we'll play with those a little bit in, I think, in this class. Not 127, but this class, I think we'll be doing that. So anyway, then there's the native API. So we've already talked, remember there was two networking libraries. There's the old-fashioned Berkeley socket library, which was WinShock, which is real low level. And then there was the high convenient one, WinINet. There's another one even lower than that, called the native API. And this is something nobody is ever supposed to use. You're not even supposed to know about it. This is for Microsoft internal use only. You're only supposed to use other ones, but it leaked out. So this is the low-level interface, and it's very popular among developers who like to have all these cool, powerful functions that Microsoft thinks are too powerful for you to use, and of course by malware authors who try to do anything unusual just to baffle analysts. So here's the game. NTDill is the library that loads in user mode, which you use to reach the kernel. You load NTDill, and that is your doorway into the kernel. You call NTDill routines, and it then calls NTOS kernel.exe, which is the kernel, and that manipulates the kernel data structures. And this is how you get into kernel mode. But you don't call NTDill directly. You call kernel32.dill. Kernel32.dill is like WinINet. It's the high-level library that exposes API calls that an application should use, and it will then call NTDill. Calling NTDill directly without going through kernel32.dill is the native API, and that is like, you know, I've knew people that would like take a running car and reach in with a wrench and adjust things while it's going. And people who like having no broken steering wheel and just have a wrench on a bolt there and everything. This is not just like using NTDill. You're running Windows directly without going through the recommended handles and interface to do it. And so that's the game. You can have an app that goes straight here, and that's what's called the native API. So it's in principle undocumented, intended only for internal use, but in fact, it's actually very easy to use WinDebug and just read the kernel and learn how it works. Nothing is actually that hidden. So, of course, they're more powerful and stealthier and less expected. So your normal user application will go here, and often your security programs will catch these calls to check to see what you're doing, like are you opening a file? So if you skip past and jump straight to the native API, you'll go past some security programs. And that's, of course, why they would really like to be in the kernel, where they can really catch everything. And that's why there's this huge battle between Microsoft and security companies over the kernel. So here's some native API calls like query system information, query information thread, and file and key. These give you much more information about processes and keys and running threads than the available Win32 calls. And NT continue will return from an exception so that you can have an exception and then continue from it anyway. Things like that would baffle people. Anyway, those are some of the tricks you can play. All right, so we're up to the last batch of cahoots, which is 7C and 126. This looks right. All right, that might be enough. I'll wait a few seconds. Aha, okay, dill pickle. I was concerned about the fact that there were no jokes on there. Didn't seem healthy. All right, so.
I'm not doing it this one.
Well, that's true, but somebody, but I think Ed is. Ed seems to be a joker too.
Yeah. Either him or me.
And Caitlin always has the funny faces.
Yeah.
All right. So, a user account more powerful than the administrator. Okay, that's system. All right. What kind of service loads ring 0 code? Those are drivers, kernel drivers. All right. How about the native API? That's ntdill. Kernel32.dill is what you're supposed to use. ntdill is the native library, native API. All right, if you divide by 0, what happens? All right, that's the structured exception handler. That's an exception. All right, so I see Vin is a winner again, and Ken Tan, and M. Hino. Okay, good. So I got my winners. So I'm going to stick around a while and see if people have questions about projects. I haven't added any new projects today, but I probably will in the next couple of days as I get my ransomware up there. And I'm going to stop the share unless anybody has any questions, which I don't see any coming in. All right, I'll stop the share and see you folks next week unless you want to stick around and work on projects. But not next week, but 2 weeks for this class. No class next week on Tuesday.